So we all know these. We all know smartphones. Smartphones have changed the world. We talk, we work, and we interact with our friends. But the tremendous success of smartphones also has caused a problem. The problem is that it is forecast that by 2018, we send about 16 exabytes of data through our mobile networks. So an exabyte is a very, very large number, and the number is shown here on that slide. And if I want to illustrate what that means in terms of content, this would equate to about 1.8 million years of high-definition video that you would send through mobile networks every month. An amazing number. Then there's an additional trend that we see is that at the moment, primarily humans talk via the internet. But we will see in the future that we also have objects that are connected to the internet. That's called the Internet of Everything. Everything is connected to the internet. And then an organization, the Worldwide Research Forum, has forecast that by 2020 we have about 1,000 wireless devices per human that are connected to the internet in one way or the other. And in order to achieve all these wireless communications, we use radio waves, microwaves, and they are using a particular part of the electromagnetic spectrum, which is between 0 and 10 gigahertz, and all commercial and military systems work in that limited bandwidth of 0 to 10 gigahertz. And this is very crowded, obviously, then. Another very important aspect of current mobile communications is that in order to be able to transmit with your smartphone, you need a base station, you need a connection to the internet, and these base stations consume a lot of power. All these mobile networks consume a lot of power, and the entire energy consumption of mobile networks is equivalent to the global air traffic. So an immense problem with energy consumption. So to illustrate that, this is a classical base station here where we have an antenna at the top. And what you see on the right corner here, this green box, this is a diesel generator. And many base stations at the moment are powered by diesel, not only in developing countries, also in developed countries like the UK, where this photograph is taken. So let's move on and see what else can we do in terms of transmitting data. And to do that, one has to take one step back. Say, what can we use to transmit wireless data? So, and that is looking at the entire electromagnetic spectrum. And if you look at that, and we will notice that a little tiny fraction, actually, of the electromagnetic spectrum at the very bottom there is used for our systems. But there is much more than that. There is the infrared spectrum. There's the visible light spectrum, the ultraviolet spectrum, X-rays, gamma rays, and so on. And interestingly, if we compare the visible spectrum, so the light, which is, again, part of the electromagnetic spectrum, this is 10,000 times larger than what we currently use in all our mobile communication systems. So there's a huge pool of resources that are available. So how do we leverage that resource? There's been the light-emitting diode, the LED, that's been around for about many years, 20 years. And in particular, we have the white high-brightness LED we see for about 15 years, entering energy-efficient illumination in the form of LED light bulbs like these. And these LED light bulbs will provide light and illumination, but the vision is that on top of that, they will provide high-speed data communication. And this is enabled by what I've called LiFi. The advantages for that, doing that, is that we have a vast amount of unregulated free spectrum in that visible light region. We have a safe spectrum. There's still some issues about health concerns with the microwave waves, but there's clearly no health concern with light, because light, as we all know, has generated life on this planet. And the other very important aspect is if we use light bulbs, light fixtures, we have already an existing infrastructure. These are hooked up to power lines, to power supplies. That exists already. So we don't have to create ever more radio cellular masts. And most importantly, these LED devices are readily available off the shelf. They are commercially available. They cost less than $3. So the question is, we have these devices, but how do we encode these data that we send in our emails and our browsing of the internet? So in order to explain the basic principle is that all data at the moment is represented as zeros and ones. So if you see a big file, that is a big stream of ones and zeros. So the way we can transmit via light bulb is simply by turning on the LED when we want to transmit a binary 1. And we turn the light off when we want to transmit a 0. And the LED is an electronic device, a semiconductor device that can switch on and off very, very rapidly. And this is done so rapidly that human eye wouldn't be able to see any changes in the intensity, and that's why it would still be constant light and data transmission would not affect illumination. That's on the transmitter side, but what about at the receiver side? So we need a device on the other end that captures these intensity changes and converts these intensity changes back into a binary bit stream in ones and zeros. So that again, we are fortunate that we have existing semiconductor devices, photodiodes, which is so shown here on the left, that would capture the intensity changes and would change them back into the bit streams in ones and zeros. And the thing is, the advantage is that these devices are very small, so we can even put them on a little semisphere and mimic an insect eye, and then have the visibility to look into all directions and capture data from all different directions, which provides unique advantages that, for example, radio frequency doesn't have. But it doesn't stop there. And this is something that we have advanced basically within the last 6 months. And I've shown transmission of a high-speed data stream at a public presentation at TED 2011, but now we have done something else. We have taken off-the-shelf solar cells. Solar cells take photons and convert photons back into electricity and energy. The question we have asked us, if that is possible, would these solar cells be able to capture the changes in intensity such that the solar cell is actually the detector for our binary bit stream? And we have had a very successful result in our labs a few months ago where we have managed to transmit a data stream of 7 megabytes, which is a typical cellular phone, when in good conditions, would be able to achieve. With an off-the-shelf solar cell, we've been able to demonstrate 7 megabytes. So this opens up an entire new field of applications, the self-powered wireless transmission. There is no energy needed. The solar cell could power your device and at the same time act as a receiver. So we believe that that is sort of complementary to the LED, and we have now a complete system that is able to solve one of these big problems, which is the energy consumption. So you might wonder what is all new about it. And I have my remote control at home to control the TV. That is using infrared, part of the electromagnetic spectrum, and that is using a very low rate bit streams on ones and zeros. In order to enhance the data rate, which is necessary in order to cope with this tremendous data surge, we need to do something else. And what we have done is we have taken, obviously, visible light and have developed algorithms that would allow transmission of binary streams, not in a single stream, but in a multiple parallel stream way. And thereby, we have enhanced the data rates very greatly. So what is the vision for that technology in the future? So it is, in our view, It will be an integral part of cellular communications, where you would have still your base station that would serve a mobile roaming in the streets and street canyons. But as soon as user enters into a room, into a house, in our view, it wouldn't make sense to be served by a radio base station outside, because the signals have to penetrate through the walls, which create a huge loss of energy from that signal, and it would be much better to be then covered by Wi-Fi. But Wi-Fi spectrum, again, is heavily limited. So therefore, if you are in a room and you are in a well-lit room, it would make much more sense to take these light bulbs to then serve these very high data rates, these very big fat data pipes. So how does it look like in reality? So take a meeting room like this. Usually you would have one Wi-Fi router installed in that room, right? That would mean that every single participant in that meeting would have to share the common resource that is provided by that Wi-Fi access point. But now, look at the ceiling. We have multiple light sources at the ceiling, and every light source has a certain limited coverage that falls into a certain seat. So it's therefore possible to have parallel streams of the same, using the same spectrum within that room. So we multiply the number of available transmission resources many times in a room, which is not possible with radio frequency communication. And that boosts what we call the area spectral efficiency, the number of bits you would transmit per unit area. That's one major step change. And the other step change is that, again, a few years ago, we have demonstrated 100 megabit from an ordinary off-the-shelf LED. So we have advanced that capability. We are now able to transmit from a single color LED 4 gigabit per second. That is about 4 times as fast as your sort of state-of-the-art high-end Wi-Fi system. So not only that, the natural question is over what distances. So we have done further experiments and have been able to show that we can transmit 1.1 gigabit over a distance of 10 meters using a single LED of 5 milliwatt, which is almost equivalent to what Wi-Fi uses. The applications that we can envisage with that technology are beyond wireless communications and cellular communications. It is beyond, when we look at the left picture there with a room. There's walls that basically confine a room, and light, as opposed to radio signals, won't be able to penetrate through walls. If I open my laptop, I see at least 15 wireless networks. But it's for sure that light can't go through walls. And therefore, it creates a more secure environment to contain signal and contain secret information. Then if you look at our appliances at home, water kettles, ovens, microwaves, everything has LED indicator lights. And these indicator lights of a device at home could be the gateway to the internet, so to connect these objects to the internet via that single LED in that unit. And as I said, 1.1 gigabit from one single LED is shown in that diagram here. Then we have shopping. We have shopping windows. Shopping windows have LED lights that illuminate the objects. But now we can blend sort of high street shopping with online shopping. These lights that illuminate can provide vital information about specifics of these objects and also what is available in the online store. In addition, and then also can provide vouchers from the store. So it's a new engagement with a customer in front of a window. So you can place your order in front of the window online while you see things. We have city councils are now changing their street lamps from energy inefficient incandescent lights to LED lights. Now we have a rich infrastructure of already existing lamp posts that we can use in order to create our future cellular networks without the need to install more ugly posts and more these expensive lamp posts and radio base stations. We have LEDs in our cars as front lights, as back lights. So we can have systems that allow cars to communicate with each other to prevent accidents. Traffic lights can talk to cars for smart transport systems and transport management systems in crowded cities. Museums. In museums, we have lights that illuminate objects very locally. But these lights can be the gateway to augmented reality, that the lights provide additional information of an object in a museum, a new experience for a customer. We have petrochemical plants, intrinsically safe environments, hospitals where, because of the antenna and the electric spark that could generate explosions, radio frequency communication is often not allowed, but you want to have secure systems that need to have wireless communications, and therefore light would be an ideal example to be used there. It goes further. Underwater communication. Radio frequency signals don't propagate underwater because it's salty, it's conductive. But light propagates underwater, so we could envisage communication systems such that divers can talk to each other with their torch. Remote-operated vehicles operating on seabeds to explore new oil resources, new resources, can take pictures of the seabed and at the same time can send them to the other remote-operated vehicles or to the surface. And then we have environments like in aircraft cabins, where usually you don't use radio frequency signals or phones. And on the other side, however, there is plenty of lights in an aircraft cabin which can be used to enhance communication in that aircraft and also to save lots of copper, lots of weight in order to make these aircrafts more carbon friendly. These are all the very good, positive advantages we can explore, but there are also misconceptions. And I'd like to address these misconceptions in a few words. There's always the question that people say, can you dim the light? And I need to say that, yes, we can dim the light and still maintain communication, uncompromised communication. Do the lights flicker? The speed at which we change the intensity is orders of magnitude higher than your computer monitor's refresh rate. So it is impossible for human eye to ever see any change in intensity using that technology. Is it for downlink only? First of all, 90% of all traffic is generated in the downlinks from the internet to the user. That's one thing. And we can also, as I will demonstrate later, use light for the uplink transmission from the device to the light fixture, to the ceiling, using infrared, for example. What about sunlight? Will sunlight disturb and interfere with that system? As I've shown earlier, the way we modulate these data is by intensity changes. Sunlight is a constant sunlight. It's very constant. And there's algorithms that could subtract that constant light, filter it out so that it doesn't have an effect. So it would even work under sunlight conditions. The other very good question that people ask is, what about indoors during daytime when you don't need the lights on? As I said earlier, we can dim lights very aggressively without compromising transmission. And that's the same we can do here. We can dim the lights to the levels that they appear off, while there still be photons emitted that are sufficient to maintain communication links. So even with lights that are sort of shut off for the human eye, it's still possible to transmit data. And a further very big misconception is that it's a line of sight technology. So you need to have a connection between the transmitter and the receiver. And I would like to show to you a video now where you will see at the end that it is not line of sight.
The Li-First offers high-speed, bidirectional, visible light connectivity. The system consists of a ceiling unit that connects to a standard off-the-shelf LED light bulb, and a desktop unit that connects to the laptop via a standard USB connection. The ceiling unit has an Ethernet and power input. It connects to the LED luminaire and modulates the visible light for the downlink. The desktop unit has a visible light receiver and an infrared diode for the uplink transmission. The system operates at 5 megabit per second in full duplex at distances of at least 3 to 5 meters. The distance and data rate depends on the particular LED luminaire that is used. The key IP of pure Li-Fi is the optimal utilization of the optical bandwidth. The sensitivity of the desktop unit means that the system functions with direct or indirect light. This sensitivity means we can dim the light to very low levels without greatly affecting the performance of our system. As you can see, the system is still transmitting at high speeds and streaming the video.
I hope you've seen that with the turned light, it was still transmitting that high-definition video to that laptop. So we believe that with Li-Fi technology, we are at an important junction that would allow us to create and maintain the tremendous increase of data rates that we all need with our new services, with the emerging internet of everything, so that we create a safer, a greener, and a smarter environment. Thank you very much.